The joint entropy of two random variables is a direct extension of the definition of the entropy of a single random variable. In this case, the analytical expression for the entropy of two random variables x and y is just the addition for all the elements in the alphabet of x and all the events in the alphabet of y of the joint probability of these events times the logarithm of the inverse of the joint probability. With respect to the expression of the entropy of a single random variable, we have replaced the entropy of x here, and we have now a double addition because we are considering the alphabets of two random variables instead of the alphabet of a single random variable. But it is a direct extension of the concept of the entropy of a single random variable. If we have two independent random variables, now the joint probability can be written as the product between the marginal probabilities of x and y, and if we replace these joint probabilities by this product between the marginal probabilities, then we can replace the logarithm of the ratio between a product in the logarithm of 1 divided by px and logarithm of 1 divided by py, just taking into account the properties of the logarithm. If we have a product there, we have an addition of the logarithms. And if now we see that the only element that depends on j is this probability of y, and that the only element here that depends on I is the probability of x, and we regroup the expressions, now here we have the addition of the probabilities for all the elements of y, and here the addition of the probabilities for all the elements of x. This is 1, this is 1, and now here what we have is the definition of the entropy of x and the entropy of y. In this case, if the two random variables are independent, the joint entropy is equal to the addition of the entropy of x and the entropy of y. But this only happens for independent random variables. The conditional entropy of two discrete random variables is a quantitative measure of information that quantifies the uncertainty that we have in the outcome of a random variable when we know the result of the other random variable, when the other random variable is known. Basically, we can obtain the entropy of a random variable if we know that a specific result has happened for the other random variable. In this case, in the definition of the entropy, we simply replace the probability of x by the probability of x given I equal to of y equal to yj in this case. And the definition of the conditional entropy is just equal to the average of this conditional entropy of x given y equal to yj for every element in the alphabet of y, for every possible of yj. In this case, we have the average for every value of y of the conditional entropy of x given this value of y, and if we replace this expression here, it's straightforward to see that the product between the probability of y and the conditional probability of x given y is equal to the joint probability between x and y, and here we have the final expression for the conditional entropy of x given y, the double addition of the product between the joint probability of x and y and the logarithm of the inverse of the conditional probability of x given y, that is added for every possible element in the alphabet of x and every possible element in the alphabet of y. If the random variables are independent, then the conditional probabilities are equal to the a priori probability to the marginal probability of x in this case, and it is straightforward to see that in this case, if the random variables are independent, the conditional probability, the conditional entropy of x given y is equal to the entropy of x. This is straightforward. Finally, we will see that there is a very close relationship between the joint and the conditional entropies. If now here we write the expression for the joint entropy between x and y, and now we take into account that what we have in the argument of the logarithm can be rewritten as a product between the marginal probability of x and the conditional probability of y given x using the base rule. And now we consider the property of the logarithm, given that we have a product here in the denominator of the argument of the logarithm, and we separate this term and this term. And now, if we take into account that the addition over the alphabet of y of the joint probability between x and y is the probability of x, what we have here finally is the entropy of x, and what we have here is the conditional entropy of y given x. Therefore, the joint entropy between two random variables is equal to the entropy of one of them, x, plus the entropy of the other one, but the conditional entropy of the other one given the first one. This can be obtained from for x as the first term here, but is straightforward to obtain the same relationship for y. The joint entropy can be written as the addition of the entropy of y plus the conditional entropy of x given y. The general result is that when we have a joint entropy between two random variables, we have the entropy of one of them plus the conditional entropy of the second one given the first one.